You might remember from your high school geometry course that there are all these triangle theorems. So you might remember letters like SSS, or side, side, side. And you might remember side, side, or angle, side, or side, angle. And what these theorems told you were that in these certain circumstances, where you know the information about the triangle in this particular order, then the triangle is going to be uniquely determined. In other words, all triangles that have those properties are equivalent to each other. And there is a situation that is a combination of these letters where that's not going to be the case. And that's going to be the side, side, angle. Now, how can we understand what's going on here? Well, let's think for a moment. Here is one side. We'll say that this is a side of unknown length. Here's our angle here. And we have side 1, we'll call that little b. And then we have side 2, little c. And the important thing about this picture is that this angle right here is the only fixed angle. This part has a fixed length, and this part has a fixed length. And if you look at this, you will notice that if we imagine this corner here being a hinge and letting this bottom part sort of swing freely, you'll see that if C is too short, we don't get a triangle. This little leg right here isn't long enough to actually connect back up to this part to make the triangle with these properties. So if C is too small, we don't get any triangles. And as we let C get bigger and bigger and bigger, there's a certain point at which we get exactly 1 value. And that's when that length is just barely long enough to make a right angle. And so C just right leads to 1 triangle. Right, now what happens if we make C a little bit longer? So let me redraw this picture again. So here's B, here's alpha. And now C is just a little bit longer than the distance from here down to there. So if it's just a little bit longer, you can see that we get 2 triangles. We'll get one going this way, and then one going this way. So C a little bigger. This leads to 2 triangles. Oops, forgot my L there. And then if we make C longer than B, so that it comes all the way out here, although this looks really, really terrible, you can see that there's only 1 triangle because there's no point of this side over here on this side for this to connect up to. So C even larger, even bigger, is just 1 triangle again. And so with this one situation, you'll notice that's not listed here among these theorems because it doesn't tell us that we have exactly 1 triangle. We actually have multiple possibilities. And this is what's known as the ambiguous case. What it basically means is that once you have the side and the angle, you do not immediately know what situation you're going to be in. There might be 1 triangle, there might be 2 triangles, there might be 0 triangles. And when there are 2 triangles, you can't tell which triangle is actually being created because both of them are possible under this restriction. And so this is the case we need to look at. And we're going to see how the mathematics of the problem actually tells us which case we're in. So here's an example. Solve all possible triangles from this diagram. Now you'll notice that this is a side-side angle. The first side is 12, then the next side is 9, and then the angle after that side is 85 degrees. And so since it's a side-side angle situation, we are in the ambiguous case. So let's first of all write down the values that we know. A, B, C, alpha, beta, gamma. So in this case, we don't know A, we don't know alpha. Beta is here, so that means 9. B is 9. And then C is 12 with gamma being 85 degrees. We're going to use the law of sines, and the law of sines is going to show us what's going to happen. So sine of alpha over A equals sine of beta over B equals sine of gamma over C. Since we don't know either A or alpha, this entire first fraction is unknown to us, so we have to just sort of ignore that for now. And let's focus on this part. We know B, we know C, and we know gamma. So this allows us to set up an equation to solve for beta. B is 9 is equal to sine of 85 degrees over 12. Right? All right, so we solve for the sine of beta. 9 over 12 times sine of 85 degrees. Now at this point, there's nothing to do except just dump this into a calculator and get a number out of it. So sine of beta is equal to 0.7471. Now here's where our past experiences need to kick in. Sine of an angle equals a number. We've done this before. If I were to draw a unit circle diagram, remember that the sine value is the y-coordinate. We want the y-coordinate to be positive. We can see that there are two solutions, a solution quadrant 1 and a solution quadrant 2. And it's that solution in quadrant 2 that tells us a lot about this problem. It tells us whether we have two solutions or one solution. If this value were bigger than 1, then we would have no solution. So here's our setup. When we plug this into a calculator, if we calculate the inverse sine of this, we're going to get the angle 48.3 degrees. To get the angle in the second quadrant, remember we have a reference angle, so that reference angle is 48.3 degrees. So we do 180 minus the 48.3 degrees, and that gives us 131.7 degrees. We still haven't learned whether or not the 131.7 is going to work, and we'll look at that in a sec. Let's just do the first part first, the 48.3 degrees. Let's put it into the chart here. Okay, so now we know two of the three angles, so we can get the third angle because the sum of the angles equals 180 degrees. So we do 180 minus 85 minus 48.3, you get 46.7 degrees. And now we need to solve for A, and so what we can do is we can set this up using our law of sines again. The choice here, in this case, we're always going to have at least one value that we've calculated. Again, I would sort of favor trying to use the original values as much as possible. So sine of alpha, which is 46.7 degrees, over A is equal to sine of 85 degrees over 12. Again, you could use the middle one, but then we're going to have some rounding error from the 48.3 degrees, and it just opens up the possibility that our numbers are going to be a little bit off. Okay, so solve for A. A is equal to 12 times sine of 46.7 degrees over sine of 85 degrees. And you plug that into a calculator, you're going to get A is equal to 8.77. And this solves one of the triangles. And we need to figure out whether or not there's a second case to look at. And so that comes back to this right here, the 131.7. Let's go ahead and start setting up the diagram, or sorry, setting up the chart. And let's see what happens here. So we had gamma was 85 degrees, C was 12, and B was 9. This was the given information. What would happen if we were to put 131.7 degrees right there? What would alpha be? And this is the part where the math tells you what's going on. Because if you're to do 180 minus these values, you're going to get a negative angle for alpha. And that negative angle for alpha tells you that that particular situation does not exist this time. There is no angle that actually makes this work. So in this case, we only get one triangle. We only get one solution. And so this is, again, the algebra, the math will tell you the answer, but you have to go through all the steps. So here's another example. Solve all possible triangles. And once again, you can see that we have a side-side angle situation. The orientation is different, but it's still relative to the parts, side-side angle. And so let's first make our little chart, A, B, C, alpha, beta, and gamma. Now in this diagram, our alpha is 50 degrees with A equal to 10. Our B is 12, beta is unknowns, and C and gamma are unknown. So we'll set this up the same way as we did before. Sine of alpha over A equals sine of beta over B equals sine of gamma over C. In this case, the C and the gamma are the unknown values, and so that fraction is not helpful to us, and so we'll work on the first two. Sine of 50 degrees over A over 10 is equal to sine of beta over 12. So if we solve for the sine of beta is equal to 12 over 10 times sine of 50 degrees. Now, just as before, at this point we have to plug it into a calculator. Sine of beta is equal to 0.9193. Calculate the inverse sine of this. Oh, before we do that, let's draw our unit circle picture. Right? So sine is equal to a positive value. And we can see that we have solutions in quadrants 1 and quadrant 2. So beta is equal to 66.8 degrees. So that's if we take the inverse sine of this. And then to get the angle of the second quadrant, we have to do 180 minus that quantity, which is 113.2 degrees. We'll look at the first case, the 66.8 case first. Right, so we have 2 out of the 3 angles. So in order for us to get the third angle, we have to do 180 minus those 2 values, which ends up getting us 63.2 degrees. And then to get C, we once again have to set up another law of sines calculation. So sine of alpha, which is going to be sine of 50 degrees over A, which is 10, is equal to sine of 63.2 degrees over C. We manipulate C is equal to 10 times sine of 63.2 degrees over sine of 50 degrees. And when you plug that in, you get 11.7 approximately. All right. So here's one possible solution. Now here's the question. Is the other case still a possible solution? So let's write in our values. A is 10, B is 12, C is unknown, alpha is 50 degrees, beta now is 113.2. And now let's think, 113.2 degrees. Is that going to work? Well, if we add these two values together, they add up to less than 180 degrees. And since they add up to less than 180 degrees, there is a value of gamma that will work, 16.8 degrees. Sorry for being sloppy down there. And we can set up another equation to solve for C. So our C value is going to be equal to, if you just follow the same algebra here, the only thing that changes will be this angle gamma here. So it would be 10 times sine of 16.8 degrees over sine of 50 degrees. And you plug into a calculator, you get 3.8. And so in this case, there are two possible triangles that work with this configuration.